Hi there, my name is June and welcome to another video of Learning with Levi. In this video, we'll be comparing all the reactions SN1, SN2, E1, and E2. If you haven't already, watch all those videos individually. We started doing a podcast format for those who'd like to reinforce the concepts on the go, and I'll link those down below. So let's start with the rate laws. SN1 as well as E1 reactions are unimolecular. SN2 as well as E2 reactions are bimolecular. Now when we say that SN1 and E1 reactions are unimolecular, we mean that the rate of the reaction is only dependent on the substrate. So when we say that the SN2 as well as E2 reactions are bimolecular, we mean that the rate of the reaction is dependent on both the reactants and the substrates. For instance, for SN2 it would be dependent on the concentration of the substrate and the nucleophile. For E2 reactions, it would be dependent on the concentration of the substrate and the base. Now let's move on to the base and the nucleophile. For SN1 reactions, you don't need a strong nucleophile. It's because the strength of the nucleophile is not important because the nucleophile is not part of the rate limiting step. And in this case, the rate limiting step is the carbocation formation. Thus, a weak nucleophile will suffice. For SN2 reactions, negatively charged species is favored over neutral charge. For the periodic table trends and nucleophiles, with rows, as you go left, it becomes more nucleophilic because the more electronegative atom holds their electrons more tightly, and then they're not likely to form bonds. For columns, it gets more nucleophilic as you go down due to the size and polarizability. For E1 reactions, a strong base is not required, while in E2 reaction, a strong base is needed. For E1, again, because the rate limiting step is the formation of the carbocation and a base is not involved in the rate limiting step, a strong base is not needed, and oftentimes the weak base will suffice, such as alcohol or water. With E2 reactions, a strong base is required because a base is part of the rate limiting step. A strong base will accept the beta proton adjacent to the carbon with a leaving group, the double bond forms, and then the leaving group leaves. Now if we move on to the substrate, for SN1, tertiary substrates are preferred over secondary, which is preferred over primary. This is because the rate limiting step is the loss of the leaving group and thus the formation of carbocation, and so we need to stabilize the carbocation. The alkyl groups help stabilize the carbocation through two things, inductive effect as well as hyperconjugation. Thus, more alkyl groups will stabilize the carbocation better. For SN2 reactions, the opposite is true. A primary is preferred over secondary, which is preferred over tertiary. The nucleophile must be able to get into the substrate and attack it. However, because as the substrate gets more crowded with alkyl groups, it gets harder for the nucleophile to attack, and we call this prevention of interactions steric hindrance. Now, a primary substrate which only has one alkyl group will react with the nucleophile faster than a secondary substrate due to the being less crowded, and so on and so on. And for both E1 and E2 reactions, they prefer a tertiary substrate over a secondary substrate over a primary substrate. For E1 reactions, the more substituted the carbocation, the more stable it is through inductive and hyperconjugation. Primary substrates will not go through E1 due to the instability of the primary carbocation. For E2 reactions, the more substituted the substrate, the more stable the alkene, which is also known as Zaitsev's product. For solvent, the SN1 reactions like polar protic solvents because they help stabilize the carbocation through hydrogen bonding. SN2 reactions like polar aprotic solvents because the nucleophile isn't as heavily solvated as it would be with a protic solvent. Now we can think of this as a concept of steric hindrance. Less hindrance, in this case the less protic solvent, the more freely the nucleophile is able to react. Some examples of some polar aprotic solvents that you'll see are DMF, acetone, DMSO, and DME. For E1 reactions, much like the SN1 reactions, the polar protic solvents are best because they help stabilize the carbocation through hydrogen bonding, and for E2 reactions, polar protic solvents are favored. Let's move on to the stereochemistry part. For SN1 reactions, you will get a mixture of retention and inversion. With the SN1 reactions, the carbocation is sp2 hybridized and planar. That means that the nucleophile can attack the carbocation from the top or the bottom, which will then give you 2 enantiomers of the product, which we call racemization. SN2 reactions do produce inverted products only. The nucleophile attacks the opposite side of the leaving group, which we call the backside attack, and when this happens, the inversion of the configuration of the carbon occurs. For E1 reactions, they do not require a particular geometry for the reaction, while the E2 reactions require the leaving group to be anti to the beta hydrogen being abstracted. E1 reactions do not require a particular geometry because the carbocation is flat. With E2 reactions, however, the coplanar arrangement of the orbitals, when the beta proton and the leaving group are anti to each other, meaning 180 degrees from each other, the reaction occurs much faster. The transition state is also lower in energy in the anti-periplanar conformation than is the syn-periplanar conformation. The last one is the rearrangement. With SN1 reactions, the first step is the carbocation formation, and the carbocation wants to rearrange to form a more stable carbocation, and that's where the hydride and methyl ships can rearrange with its bonding electrons to form a more stable carbocation. With SN2 reactions, because there's no carbocation form, hydride and methyl ships do not occur. With E1 reactions, rearrangement can occur, while E2 reactions, no rearrangement is possible. With E1 reactions, they form a carbocation. Again, the carbocation can rearrange to form a more stable carbocation through hydride or alkyl shifts. E2 reactions, they are a concerted reaction and they do not form a carbocation, thus no hydride or alkyl shifts can occur. The last bit is on the bottom right corner where it says heat favors elimination reactions. Now this is particularly a particular statement that pertains to E1 and SN1 when they're in competition. Low temperatures will push it towards SN1 and higher temperatures will push it towards E1. Now, this concludes the E2, the comparison of the SN1, SN2, E1, and E2 reaction videos. Down below are the flashcards of all topics within the SN1, SN2, E1, and E2 reactions. Now, if you're interested in that, we'll link those down below. Hit that like button, that subscribe button, support the channel, share it with your friends who need help with organic chemistry. In the next video, we'll be looking to see how to pick a reaction depending on the criteria that's given. So I'll be giving more videos on that. So let me know down below what you'd like to see. Social media links will be down below, and as always, remember, you gotta go.